Hello everyone, in this video we will analyze the complexity of the backtracking line search algorithm when used in the gradient descent for L-smooth and convex functions. Let us begin with the oracle complexity result for backtracking line search algorithm. Recall that the backtracking line search algorithm used the iterates xt plus 1 equal to xt minus eta t times gradient f of xt, and which uses the following routine to select eta t at the tth iteration. We start with eta t1 equal to 1, and then there are several steps, and at the kth step we are breaking if this condition is true. The condition is that f of xt minus eta t k gradient f of xt less than f of xt minus alpha times eta t k times norm square of gradient f of xt square. Otherwise, if this condition is not true, then we continue, but this time we decrease eta by a factor of beta. So eta t k plus 1 is equal to beta times eta t k, and continue. The important thing to remember here is that the stopping criteria, which we will use with alpha equal to half and beta less than 1. Let us now derive the oracle complexity bound for backtracking line search gradient descent algorithm. The result is that under assumptions a1 and a2, which say that the function is smooth and convex, the oracle complexity of backtracking line search is given by t is equal to b over 2 epsilon times max of 1 comma L by beta. So as compared to the constant step size gradient descent, whose complexity was bl by epsilon, this is approximately of the same order. It is in fact very close if beta is close to 1 and L is something greater than 1. So backtracking gives us a similar oracle complexity bound, but this time we do not know L. There is some penalty for not knowing L, but that is very small. So let us look at the proof. The first step of the proof here is determining the smallest value of eta that we can have. Note that eta starts with 1 and is reduced by a factor of beta at every iteration. So eta t of k is actually beta raised to the power k minus 1. So how long would this reduction continue, and is it possible for eta t to become very small? So can eta t tend to 0? In that case, the progress would stall. So to answer this question, we look at two conditions. The first is the stopping criteria of the backtracking line search. The search will continue as long as we will satisfy f of xt minus eta t k gradient f of xt greater than f of xt minus alpha times eta t k norm of f of xt square. And if this condition is violated, we stop, because it means that we have achieved significant decrement. So this is a condition that we have not achieved the required amount of decrement. The next is the quadratic upper bound inequality, which we have already derived in the step 3 of the constant step size gradient descent proof. It said that f of xt minus eta t k gradient f of xt less than equal to f of xt minus eta t k 1 minus eta t k L by 2 norm of f of xt square. So if we were to take a step using the current value of eta t k, at which point the algorithm has not terminated, then this inequality would hold. So all we need to do is to combine these two. If we are in an iteration that satisfies both of these inequalities, which means that the backtracking line search has not terminated yet, then we have that eta t k is greater than equal to 1 over L. So this holds for all inner iterations at which the backtracking algorithm is still going on. But at some point the search stops, and this would not hold. So suppose that the search stopped after k plus 1 iterations. Then the condition was true till the kth iteration. But our update rule for eta was multiplication by a beta factor. So therefore, the final value of eta t is equal to eta t of k plus 1, which is equal to beta times eta t of k. So which is greater than equal to beta over L. So that is the final condition that holds at termination of the line search procedure, and we end up using this eta t value in the main gradient descent update. There is a possibility that the line search does not even start because the requirement is violated right at the start. This would happen if L is too small, and in that case eta t will be equal to 1. So generally we can say that eta t is greater than equal to eta min, where eta min is the minimum of 1 comma beta over L. So this also makes sense. As per our motivation, we said that we wanted to find a value of eta that is not 1 over L or smaller, because the problem dependent L was too large and led to a very small step sizes. We were in fact hoping to work with larger step sizes. We see now that that is exactly what is happening in line search, that we will end up with some eta t that is greater than equal to beta by L and could even be larger than 1 over L. The downside is that it is possible to have eta t equal to beta by L for some problems. This is essentially the worst case scenario for backtracking line search and occurs when the quadratic upper bound is tight. So if that is the case, you can see that it is quite possible for the step size to be equal to 1 over L at iteration k minus 1 and therefore become equal to beta by L at iteration k. So in other words, the backtracking line search will not always select a large step size, and in certain situations it will select a step size that will be slightly less than 1 over L. Next, let us go to the second step, which is exactly the same as the first step of the constant step size gradient descent. We begin by expanding xt plus 1 minus x star square, which is equal to xt minus x star square minus 2 eta t, inner product of gradient f of xt minus x star plus eta square gradient f of xt norm square. And then we are substituting this property of smooth convex functions, which we derived as minus 2 eta t, inner product of gradient f of xt minus x star less than equal to minus 2 eta f of xt minus f of x star minus eta by L norm square of gradient of f of xt. So as to obtain norm square of xt plus 1 minus x star less than equal to norm square of xt minus x star minus 2 eta t f of xt minus f of x star plus eta t times eta t minus 1 over L norm square of gradient of f of xt. So here is where there will be a departure compared to the constant step size case. Recall that we dropped the last term by assuming that eta was less than 1 over L. Now this is no longer the case here. The eta t may not be less than 1 over L. In fact, we were trying to prove the opposite. So the last term is not necessarily negative. Instead, we have to use the backtracking stopping criteria now. So let us keep this inequality with us for now and go to step 3. Let us write down the stopping criteria of the backtracking line search algorithm, which is that f of xt plus 1 less than equal to f of xt minus eta t by 2 gradient of f of xt norm square. Subtracting f of x star from both sides, we get f of xt plus 1 minus f of x star less than equal to f of xt minus f of x star minus eta t by 2 norm square of gradient f of xt. Now let us combine this inequality with the one that we have obtained in the previous step. To do so, multiply it by 2 eta t and rearrange so as to obtain minus 2 eta t f of xt minus f of x star less than equal to minus 2 eta t f of xt plus 1 minus f of x star minus eta t square norm square of gradient f of xt. So all we have to do now is to add the inequalities so as to obtain xt plus 1 minus x star's norm square less than equal to xt minus x star norm square minus 2 eta t f of xt plus 1 minus f of x star minus eta t by L gradient of f of xt square. So we have been able to remove the last positive term and therefore now the last term will actually be negative. So this is our one step inequality. So we drop the last term and then also use the bound eta t is greater than equal to eta min, which is equal to min of 1 comma beta over L, so as to obtain xt plus 1 minus x star square less than equal to xt minus x star square minus 2 eta t f of xt plus 1 minus f of x star, where now we can bound minus eta t with minus eta min so as to get xt plus 1 minus x star square less than equal to xt minus x star square minus 2 eta min f of xt plus 1 minus f of x star. So the only difference between what we get for backtracking line search and for gradient descent is that here f of xt is replaced with f of xt plus 1. But this is not a big change, and as we will see later, this will not matter much in the entire analysis. So finally, the step 4 is the application of the telescopic sum as before, so as to yield sum over t is equal to 2 to capital T. So here we have a sum from 2 to t. F of xt minus f of x star less than equal to 1 over 2 eta min norm square of x1 minus x star square minus norm of x capital T minus x star square. So here we summed from 2 to capital T because we do not have f of x1 on the left. So dropping the negative term and using the bound on x1 minus x star norm square, we obtain that sum over t is equal to 2 to capital T, f of xt minus f of x star less than equal to b over 2 times eta min. Now in this case, the backtracking algorithm already ensures that the function value is non-increasing, so we don't have to explicitly prove it. So finally we have that f of x capital T minus f of x star is less than equal to b over 2 times eta min capital T, which is the required performance bound. So if we set it equal to epsilon, we will get t is equal to b over 2 times eta min epsilon. So which is the required oracle complexity. One question that might arise from this analysis is that why is backtracking line search not giving a better oracle complexity as compared to constant step size gradient descent algorithm? Why are both the oracle complexities almost same? Recall that after all we argued that the L value of the problem may be too large and therefore the choice of step size eta equal to 1 over L would be too small for many algorithms, especially in the vicinity of x1 and x star. We have seen that backtracking line search indeed gives us a step size of greater than equal to beta over L, where beta is close to 1. So why is oracle complexity not better? It is in fact a subtle point, and understanding the answer to this question holds the key to understanding the limitation of this kind of analysis. The key point is that there are problems where the step size obtained by backtracking line search will actually be as low as 1 over L. Then for these problems, both the algorithms are exactly the same. Therefore, for such problems, we are sure that selecting the step size to be constant or using backtracking line search to determine the step size will not make a difference because both turn out to be same. Of course, there are other problems where backtracking line search will beat constant step size gradient descent by selecting higher step sizes. But a key point to observe here is that the assumptions made do not make any distinction between these two classes of problems. Both classes of problems involve smooth convex functions and same parameters b and L. So to repeat, backtracking is only better than constant step size gradient descent for some problems. However, since all problems have same parameters, the entire analysis is oblivious to this distinction between these two classes of problems. Further, the oracle complexity is a result on the entire class of problems covered by these assumptions. In other words, since backtracking is only better for some problems, its oracle complexity for the whole class of problems cannot be better. The oracle complexity of an algorithm can only be better if the algorithm is better for all problems in that class. But this does not mean that backtracking is no better than gradient descent. For a vast majority of problems, you will see good empirical performance at the very least. But to obtain better oracle complexity bounds, we need an additional assumption that would separate out the problems where the performance of constant step size gradient descent is bad and that of backtracking is good. For instance, if we assume something about the dependence of L on X, then maybe it might be possible to show that under such an assumption, backtracking gives theoretically better performance. In summary, the oracle complexity bounds will always reflect the general performance over the entire class of algorithms. Further, you could narrow down the class by making additional assumptions and then developing new algorithms for those assumptions. That is, if you put more restrictions, then more the algorithm will be specialized and more you can improve it, So this is in fact commonly done for many algorithms. So in summary, there is a fine balance between how many assumptions you want to make and how generally you want the algorithm analysis to be applicable. So that concludes our discussion on backtracking line search for selecting step sizes in gradient descent. We have seen the intuition of the method as well as the oracle complexity bound for smooth convex functions. So that is all for this video. In the next video, we will look at the application of gradient descent to general smooth objectives that could be non-convex.